Okay, so for the past decade or so, two absolutely world-changing technologies have been rising up on these parallel tracks. On one side, you've got Bitcoin, this idea of decentralized digital gold, a trillion-dollar vault built on what we thought was unbreakable math. And then, on the other side, you've got quantum computing, a totally new way of thinking about calculation, so powerful it promises to solve problems our best supercomputers couldn't crack in a billion years. So what happens when these two forces finally collide? Well, you get a trillion-dollar question. Can the ultimate master key unlock the ultimate digital vault?
And that right there is the heart of the conflict. You have Bitcoin, the unbreakable vault. It's secured by mathematical problems that are so ridiculously hard a normal computer would literally need longer than the age of the universe to solve them. No joke. And then you have quantum computing, which is basically a theoretical master key designed to solve exactly these kinds of impossible problems. It's a high-stakes cryptographic race, for sure. The strongest lock ever made versus a key that could, theoretically, make it all worthless overnight.
So what really happens when this unstoppable force meets this immovable object? Is it as simple as quantum computing just killing Bitcoin? Well, the answer isn't a simple yes or no. It's actually a really fascinating story about timing, about mathematics, and about a defense plan that's already in the works. And that's exactly what we're going to unpack today.
Okay, let's dive in. To really get a handle on the threat, we first have to understand how Bitcoin's digital vault, how the lock, actually works. The security of your Bitcoin really just boils down to two things: a private key and a public key. Your private key is everything. It's the secret password you have to protect like your life depends on it, because it's the only thing that can actually unlock and spend your funds. Now, from that private key, a one-way mathematical function creates your public key. And the best way to think about a public key is like a transparent safe deposit box. Anyone can see it, anyone can put Bitcoin into it, but only your private key can open it. The whole system is safe because it's super easy to go from your private key to your public one, but it's basically impossible for a normal computer to go backwards. And that is where the quantum threat comes in. See, back in 1994, a mathematician named Peter Shor came up with this algorithm for quantum computers. And Shor's algorithm is this brilliant but also kind of scary piece of math, designed to do one thing incredibly well: find the prime factors of huge numbers. And it just so happens that's the exact mathematical problem that protects not just Bitcoin, but most of the internet's encryption. It's the specialized lockpick designed for the one lock everyone thought was completely unpickable.
So, picture this. How would a quantum heist actually go down? Well, the window of opportunity is surprisingly small. Step 1. An attacker needs to grab your public key, which only gets broadcast across the network for a short time when you go to make a transaction. Step 2. In the 10 minutes or so before that transaction gets confirmed, they have to race against the clock, running Shor's algorithm on a massively powerful quantum computer. And if they pull it off, they get to Step 3. Boom. They figured out your private key. They can then sign a new transaction, send all your funds to themselves, and your money is just gone. Game over.
Now that sounds absolutely terrifying, I know. But we need to be really precise here because there are actually two main quantum threats people talk about, and it's so important to separate the real, serious danger from the hype. One is potentially fatal to the system, the other is more of a nuisance.
And this slide lays out the two attack vectors perfectly. First, you've got stealing funds with Shor's algorithm. As you can see, the impact is listed as fatal. That's the existential threat we've been talking about. But then there's the second threat, disrupting mining with a different tool called Grover's algorithm. And look at the impact there. Just a nuisance? So why is that one so much less dangerous?
Well, think of Bitcoin mining as a giant global lottery. You have millions of specialized computers all guessing numbers as fast as they can, hoping to win. Now, Grover's algorithm could give a quantum computer a massive speed up in this guessing game. But here's the crucial part. It doesn't break the lottery, it just creates a much faster player. And Bitcoin has this brilliant built-in immune system for this exact problem, called the difficulty adjustment. If miners start winning the lottery too quickly, the whole network automatically makes the puzzle harder for everyone. So a quantum miner just forces the network to recalibrate. It creates a new arms race for sure, but it's not a system killer.
Okay, so we've established that the real fatal threat is someone stealing your money with Shor's algorithm. And that brings us to maybe the most practical question of all. How much time do we really have before this so-called doomsday clock strikes midnight?
And here is the number that should help everyone take a deep breath. The general consensus among quantum experts and cryptographers is that a machine powerful enough to actually break Bitcoin's encryption is at least 5 to 10 years away, and honestly, probably even more. So you don't need to panic. The threat is definitely on the horizon, but it is not at the gates. We have a window, a good amount of time to prepare. And to understand why that is, you just have to look at where we are on the quantum timeline. Right now, we are smack in the middle of what they call the NISQ era. That stands for Noisy Intermediate Scale Quantum. Basically, today's quantum computers are like the giant room-sized computers from the 1940s. They're massive, they're super expensive, and they make a ton of errors. To break Bitcoin, we need to get to the fault-tolerant era. That's going to require machines with thousands, maybe millions of stable, error-corrected quantum bits or qubits. There's just a huge engineering gap between where we are today and where we need to be for that to happen.
So, we have a real threat, and we have a 5 to 10+ year timeline. The really good news is that cryptographers aren't just sitting around waiting. They're already building the defense. So, what exactly is Bitcoin's quantum shield? How does it work?
The solution has a name. It's called Post-Quantum Cryptography, or PQC for short. This is a whole new family of encryption methods that are built on different, way more complex math problems, ones that we believe are hard for even a powerful quantum computer to solve. But here's the most important part to get. These new algorithms are designed to run on the classical computers we all use right now, today. And that's really the key takeaway. You don't need a quantum computer to fight a quantum computer. This isn't a race to build our own quantum defensive shields. No, it's a software problem. The solution is simply upgrading our existing systems with new quantum-resistant software. We're fighting a future hardware threat with a present-day software solution.
So what would this upgrade actually look like for you, a user? Well, it would basically kick off something you could call the Great Digital Migration. The best analogy is how we all switched from those old magnetic stripe credit cards to the new chip cards. Once the Bitcoin network gets upgraded to support these new quantum-safe addresses, every user will just need to make one simple transaction: move their funds from their old, vulnerable address to a new, quantum-safe one. That's it. Once your Bitcoin is in the new address, it's secure.
So let's just do a quick recap of the big picture here. The real #1 threat is theft using Shor's algorithm. The threat to mining, on the other hand, is basically a manageable arms race. The good news is, we've got a solid 5 to 10, probably more, year window to get ready. The solution is a software upgrade called Post-Quantum Cryptography. And finally, putting it into action is going to require everyone to do this digital migration of their funds to new, safer addresses. Which brings us all the way back to our final question. You know, the dawn of quantum computing isn't necessarily the end of Bitcoin. In fact, it might be the very thing that forces it to evolve and get even stronger. This challenge is going to require the entire global community to coordinate on a massive upgrade that will make the network more resilient than ever before. So is this the threat that finally breaks Bitcoin, or is it the catalyst for its greatest evolution yet? The race is on, but the defense plan is already in motion. Thanks for joining us.